We've now laid the foundation for considering an arbitrary thermodynamic model and deducing all of its consequences. Now, the ideal gas is one such model, and it's useful to know all of its properties, but it's not really the heart of thermodynamics, right? The potentials and the derivatives, response functions, stability, the model is what thermodynamics is. The way that models relate to predictions, that's what thermodynamics is. The ideal gas is just one specific case. So is the Einstein solid, so is the two-state system, so is anything else. But some cases, some specific models are so insightful that they really tell us something more about how thermodynamics works internally that we might not have noticed. The van der Waals model for a gas is one such model. It illuminates phase transitions in a way that we might never have noticed if it hadn't been proposed. Actually, at the time when van der Waals proposed this model, there was debate about whether thermodynamics, with its nice, clean, beautiful derivatives, could ever describe something messy and discontinuous like a phase transition. But van der Waals showed that this model can, and it's based off of very simple physical assumptions. Now, before I write something down, I wanted to do a disclaimer. The van der Waals model is not a better model of gases than the ideal gas. It's just a different one. It's also not particularly accurate when it comes to a quantitative prediction. However, it includes the essential features that give us a liquid to gas phase transition. And so it's very important to study this so we can understand what really underlies these kind of miraculous events called phase transitions. So the van der Waals model will follow the way that was initially proposed. It starts by proposing some modifications to the ideal gas equation. The first modification, here's our ideal gas equation. The first modification is, in order to describe a more realistic gas, van der Waals realized that there must be some accounting of interactions between the gas molecules or atoms. Normally, these interactions would be positive. They repel each other and push each other away. But at some point, he realized that when the density becomes large enough, the molecules will spend more time closer together and will have some region where they ultimately attract each other. And so the first modification to the ideal gas equation is to add a term which acts as an attraction. It has the form of a constant A that depends on the in principle, this depends on what molecules it is, but not on the state variables. The constant A multiplied by the density squared, the number density squared. It's subtracted from the ideal gas pressure, and this means that when the density becomes large, the pressure, external pressure, is reduced from its ideal gas prediction because the molecules are spending more time pulling each other together. As soon as the density gets high enough, then this term takes over and it just crunches everything down to an infinitesimal size. So van der Waals realized that that was no good and added a second term here. Instead of dividing the thermal part by just the volume, van der Waals imagined that in a real gas, there would be some minimum volume beyond which it couldn't be compressed. Once the molecules get so close together that they're basically touching, then they wouldn't be able to really get compressed anymore, and so the pressure should go really, really high as we approach this limiting volume. So the limiting volume is dependent on how many molecules are in the system, and so we divide by V minus Bn, so that this term has a vertical asymptote when V equals Bn, rather than when V equals 0. This means that this term at a low volume, just above Bn, will dominate and keep the gas from compressing to an infinitesimal size. So this is the van der Waals model. It's determined by two constant parameters, A and B. A represents attractive forces, and B represents a hard repulsive core. Now let's look at what is generated from this equation on a PV plot. If we have a situation at very high temperature and very low density, then these terms, the modifications are really not important. So at high temperature and at low density, a curve in the PV plane at constant temperature looks just like the ideal gas law. But let's consider what this might look like if we have a low temperature. Well, at a low temperature, this term is much more important, and it's negative. So there's going to be an increase slightly because volume is going down. This term is going to start. This term will be positive, but it will be getting larger as volume decreases. When the volume is still large, this term looks like ideal gas, but this term doesn't come into play. But eventually there will be some point where this term starts to become important. The volume has gotten so low that this term becomes important, comparable to these, and there's a subtraction between these. So this might actually spend some time going down for a low temperature isotherm. So we'll see that this curve could actually become negative at some point. A negative pressure is unphysical, but it's not really that concerning. It's already sloping down, which makes it unphysical because of the condition on the compressibility being positive. So this might slope down for a while, but then eventually it's going to get to this volume equal to B times N, where it has a vertical asymptote. So it will shoot back up like that to have that vertical asymptote happen when V is just a little bit larger than NB. All right, and somewhere in the in the middle between these, an isotherm might look something like that. So this green one, I'll just label this here for consistency, medium temperature. All right, so that's what the van der Waals equation of state looks like if we plot it for various values of temperature at some specific A and B parameters. Now, let's think about what this kind of behavior might mean. Remember that one of our conditions for stability was that the derivative of pressure with respect to volume had to be negative. That means a system can only be mechanically stable if this isotherm is sloping down. For the red curve, it's sloping down everywhere, so this one is always stable. For the green temperature, it looks like it might get close to a zero slope at some point, but still it's sloping down everywhere, so it's still okay. It has this weird kink in it, but it's still stable. At this low temperature, though, we have a problem. In the region where the curve has an upward slope, so between here and here, we have a region of instability. And that instability means that if we somehow began a system in an initial state right here, it wouldn't stay there. Mechanically, it would shrink or it would grow and get to one of these sides where it starts to become stable. So we have this forbidden region for volumes on the van der Waals gas model, and it looks kind of weird, right? we don't quite know what that means yet. So let's answer a question now, which is going to be important to our calculations with this. So there's this region of instability here on the low temperature. There's no instability on the high temperature. It looks like this green curve, might just barely get to an unstable region in the middle where its slope is 0, but it never really gets there. And we can imagine that if we go lower temperatures between here, there's some unstable region, and as we continue to decrease temperatures and draw colder and colder isotherms, that this region of instability doesn't really go away. So the question is, where does this instability begin? So where does the region of instability begin? So what determines that? Well, a region of instability has a section of the graph where the derivative of dp dv is positive. Okay. So up here on the red curve, the derivative dp dv is always negative. Here, it's always negative, except for maybe a very small region or one point where it's 0. And then down here, it switches. The derivative switches from negative to positive to negative, right? So we have a change in sign of the derivative of these isotherms. If the derivative has a change in sign, then that's where instability starts. On this green isotherm here, then, what we have is if we look at what the derivative is doing, it's negative. It barely gets down to 0, and then it looks like it might become a positive slope, but it doesn't. It goes back and stays negative. So this special point right here, the derivative of the graph is 0, and the change of that derivative, right, how the derivative is changing, is also momentarily 0. So what we have right here is actually what's called an inflection point. And at an inflection point, we have the second derivative of the curve equal to 0. So here we're looking for the special, so there's an inflection point here. There's inflection points, there's an inflection point there also, right? The second derivative is 0, it changes concavity. The inflection point is there too. We're looking for the special inflection point where the function is also flat, right? Special inflection point where the function of pressure of volume is also having 0 slope. An inflection point is where it changes concavity. It could change concavity and just stay negative slope the whole time. It could change concavity and then have a positive slope in between and then negative later. But it could also change concavity and just barely have a 0 slope at that point. And that's where this unstable region begins. So let's take these two equations. These define the sort of the maximum temperature where we would see an instability. And let's try to solve these for the van der Waals model. So I'm going to write out the derivatives of this pressure function then and set them equal to 0 to solve the system. So for the first derivative, negative nkt over v minus bn squared plus 2an squared over v cubed. That is set equal to 0. Second derivative will be 2 nkt over v minus bn cubed plus minus 6an squared over v to the fourth. This will be equal to 0 as well. So this is the system of equations that I have to solve. the way I'm going to interpret this as a system of equations for a temperature of the critical temperature for the instability to start, and the volume that inflection point sits at. First, let's solve for the volume. That's going to be easier. I'm going to try to set these equations up so I can add them to eliminate the second terms. First, let's multiply the top equation by 3. So 3, 6. And then we'll divide the top equation by v. So I'll put a v there, and we'll change this to the fourth. All right. Then when we add these together, we're going to get minus 3nkt over v times v minus bn squared plus 2nkt over v minus bn cubed. So that's supposed to be equal to 0. These two terms cancel out. Right sides were all 0. Okay, so this is pretty fortunate here. We've got nkt in the numerator in both terms. It's equal to 0, so we can cancel that off. We also have this v minus bn here in the bottom. This side it's squared, and this side it's cubed. So I can get rid of that with one power left over. So what I'm left solving there is minus 3 over v equals 2 divided by v minus bn. So we'll just leave it down here to get this solution finished. I'm going to move the minus 3 over v to the other side. So we'll have 3 over v like that. And then I'll cross multiply, so I'll put a v up here. And I'll put the v minus 3bn up there. Okay, and then we will basically move the 2v over to this side, so minus there, and then move the 3b over here. Okay. So our region of instability begins at a specific volume, and we'll call this the critical volume, Vc, is equal to 3bn. Okay, so we've got that part figured out. And then we'll go back to our original equations here. So there was a 1 there, there was a positive 2 here, and this was v cubed. Okay, so we know that 3bn now is the solution for v to these equations. So these are actually all VCs. And let's plug in. So over here, 3bn minus bn will be 2bn. And when I square that, I will get 4 b squared n squared. Here, when I cube this, I have 3 times 3 times 3 is 27 b cubed n cubed. And I don't really need this second equation anymore because both of these will give me the same solution for t. So let's just work with this one now. Canceling what we can. Let's see. All right, there's an n on the numerator and denominator there. There's an n squared and an n cubed there. Both equations are divided by n, and it's equal to 0, so I can just ignore that. Both equations are divided by b squared, so I can ignore that. Then let's move the kt over 4 to the left side to the right side by adding, like that. And then we'll multiply both sides by 4. So k times t to solve that equation is 8a over 27b. So we'll call this the critical temperature, and it doesn't matter to move the Boltzmann's constant k around. It always multiplies the temperature in this every place it shows up. So I just prefer to write this as k times Tc will be equal to 8a over 27b. All right, so we'll keep a track on that one as well. All right, that's correct. The last one that we'll do is, so this was the temperature of the isotherm. Remember what we're doing here. We've got a graph of pressure versus volume, and we're looking for this special isotherm that has an inflection point at the same place that it has zero slope. So this volume VC is where that occurs on the horizontal axis, VC. It's 3 times Bn. So Bn is where that vertical asymptote was for the PV curve. VC is three times that. So it's close in there. Tc was the temperature that generates this isotherm. So isotherm at temperature equals Tc is the one that has this property. So temperatures above this will not have any instability at all. Temperatures below this will have some region of instability. The last thing to find out is what this pressure is here. The pressure, the vertical component, the vertical coordinate of that dot. So we'll plug in here, we'll say Pc is equal to Nk Tc over Vc minus Bn minus An squared over Vc. So we basically just plug in the temperature and the volume of that point to our van der Waals equation. So what's this going to come out to? I'm going to put everything in terms of the B, A, B, and N here. So KTC was 8A over 27B. V is 3BN, so minus BN gives us this 2BN. And then minus AN squared over V squared. So 9B squared N squared. Okay. Critical pressure then, let's just divide here a bit. So the I'll just rewrite. So we've got 8 over 2, so that's a 4A. Then we've got 27 in the denominator. There's 1B here and 1B here, so B squared. The n's cancel. Then we have minus A. The n's cancel. We have minus A over 9B squared. So we'll get a common denominator by multiplying the top and bottom here by 3. 3 times 9 is 27. And then 4 minus 3 is 1. So we get A over 27B squared. Okay, so that's our pressure at this inflection point, A over 27B squared. Okay, so what we see here is that this point essentially just depends on the number of particles in the system, but not the density, right? If I divided n on both sides, then this would be that a density equals 3b, or like volume per particle equals 3b. So the location of this point basically just depends on the coefficients a and b, the parameters of the model. So what we're going to do next with this is kind of an ingenious trick, and it's actually quite important to the fact that the van der Waals model is applicable to most systems. Why is it a good model? So let's look at this equation here, and this is all in terms of like the actual measured pressure, the actual measured volume, the actual measured temperature. Let's instead write it in terms of values that are proportional to the critical values. So I'm going to define a lowercase t will be T over Tc. So in terms of lowercase t, this dot will always be on the isotherm where T equals 1. Let's define a lowercase pressure, which is equal to P over Pc. And in terms of this lowercase pressure, the dot is always at a vertical coordinate of 1. For the volume, I'm not, I think, actually going to define it relative to the critical, It's possible to define it as, so V over Bn, and then just have things happen at V equals 3. I actually am going to define it so V equals V over Vc. So we'll put it like that. So everything is relative to this critical point here. It occurs at a horizontal component of 1, vertical component of 1, and a reduced temperature of 1. So these are called reduced variables, by the way. I'll let that slip in. And let's express the equation of state in terms of reduced variables. So how can I do that? Well, my pressure is equal to Pc times lowercase p. My temperature, KTc, is equal to lowercase t times KTc. On the bottom here, I'll have Vc times lowercase volume minus Bn. And then over here, I'll have AN squared, that doesn't change. Critical volume squared times reduced variable volume squared. All right, so let's try to simplify this then. On the left side, first I'm going to replace my PC. So 8 over 27 B squared times lowercase pressure, reduced pressure. Then up here I'll have N times reduced temperature. K times the critical temperature is 8A over 27B. The critical volume is 3BN times the reduced volume minus Bn. Then in the second term, it's a bit simpler. I'm just going to have 9 B squared N squared times the reduced volume squared. Okay, so that's kind of nasty looking. Let's see if we can improve this at all. So let's make some simplifications here just by erasing. First of all, the extensive variable is only n. So there's an n on the numerator and both terms in the denominator here. That's great. That means I can get rid of it. We shouldn't expect any intensive variables to appear anymore. This equation, in terms of reduced variables, relates only the intensive variables. So no extensives. Same thing happens over here. Good. There's an n squared in the bottom and an n squared in top. All right. So what else can we do? I see one other thing. Oh, I've made a mistake here. This a is not squared. It was just an squared. There's only an a there. So every term has 1 power of a in the numerator. So these a's, surprisingly, can actually be canceled off of each term, as long as the a isn't 0, which would be kind of dumb. So the a's are gone. What about the b's? Actually, we've got e squared in the bottom here, b squared in the bottom here, and then we have one b in this denominator, but another one there. So the b's can actually cancel out as well, right? All the b's, if we multiply the equation by b squared on both sides, they will go away. So that's also valid as long as b isn't 0. Cool. So this one turned into 1. All right, and then we've got these 27s here, so let's multiply both sides of the equation by 27. So times 27 over there, times 27 here, and times 27 here, we'll put 27 over 9, so that will be equal to 3. So this is an 8. This 8 was multiplied. Okay, so our van der Waals equation of state in terms of reduced variables is the reduced pressure is 8 times the reduced temperature over 3 times the reduced volume minus 1 minus 3 over the reduced volume squared. That's it. Van der Waals equation of state in terms of reduced variables. Now, the remarkable thing about this is that all appearances of the parameters a and b have disappeared. So in terms of reduced variables, there is a universal behavior to this model. That means that all van der Waals gases, no matter their values of A, B, or N, can be described within the same theoretical framework. We can use the reduced variables to do all of our theoretical work, and then when we want to turn it into a prediction for a real system, we only have to decide what are the values for A and B of that system and scale it up for each variable accordingly. So that's the van der Waals model in terms of reduced variables. Its critical point, above this temperature there is no instability, and below this temperature there is. The critical point is related to the parameters A and B. And if we rewrite the equation of state in terms of reduced variables, it has a universal format that's called actually, I should say that for most models that have a critical point, a point that divides unstable to unstable and stable, for most models that have a critical point, if you express them in terms of reduced variables, you will get an equation that does not depend on the parameters A and B that define the critical point. So that's called the law of corresponding states, is that any physical state of a real system could correspond to some universal state in terms of reduced variables. So that's the van der Waals model of the gas.